The first thing is I just want to show you that this is just not only theory, but that it works well in practice. So this is a toy problem, and of course people are applying these techniques to other things than toy problems, but just to give you a sense of what you can do on toy problems. So here we have a matrix which is 1000 by 1000 of rank 2. And I'm making this matrix at random, so it's you can think about it as a low rank random matrix. And things are done so that when you look at the matrix, the entries of M, because it's random, they have mean 0 and standard deviation about 89, which means that the signal is kind of low, like most of the entries are below minus 89 and minus 0.89 and plus 0.89. And I'm going to do something just to show you that this is robust vis-a-vis noise. I'm going to show you not this matrix, but it's a matrix corrupted by white Gaussian noise. And the noise is actually quite strong. It's actually overpowering the signal in the sense that there's more noise power in any per entry than there's signal power. Since the power of the signal is 0.89 squared, which is probably like 0.8. And the noise power is 1, so there's more. Actually, the entries are dominated by noise. Nevertheless, and I'm going to show you only 20% of these entries. I'm going to remove 80% of all these entries. So I show you 20% of extremely corrupted entries. And then when I run this algorithm and I average over 20 trials, this is what I get. I get that the recovery M hat minus the truth divided by the number of entries is 0.05. And so we see two things from this figure of merit. We see that not only we guess all the entries we've not seen very well up to accuracy 0.05, but on top of this, even the entries I've seen, I reduce the noise level by a factor 20. So it works. And just to show you that the theory is robust vis-a-vis noise, which there are two ways. I mean, the first question you have to ask when you do something like this is, can you deal with the fact that the matrices of interest are not exactly low rank, but only approximately low rank? That's question one. And can you deal with the fact that typically you're not going to observe perfectly entries, but they're always going to be corrupted by some small amount of noise? And you can deal with both non-idealities, and the way you deal with noise has been worked out completely in the literature. What you do then is you minimize the nuclear norm. Now you relax your condition. It's useless to assume that to find a matrix that fits what you've seen, because what you've seen is noisy. So you ask to be within the noise level, and within the noise level only. And what you can prove is you can prove that the mean squared error is low. That is, the mean squared error per entry is essentially proportional to the noise level, and things are well. And numerically, you can see this way, which is even though the entries are not observed noiselessly, but they're observed with quite a bit of noise, and the method would just remove the noise and give you accurate estimates. When you try this on real data sets, for example, just as a toy example, we took a data set on the web of temperatures around the world, daily averages at 1472 locations around the world in 2008. And any reason why we took a data set that looks like this? No, because it's just 2008, so because of course it's low rank. What should be roughly the rank of this matrix? 20. Ideally, it should be something like 2, right? Because there's rank 1 because of the northern hemisphere, then you have the southern hemisphere, and over there everything else is correlated pretty much. So the rank should be low, and in fact it is kind of low. As you'll see, we withheld 70% of the entries, and when we are trying to predict all the entries we withheld, we got a mean squared error of a relative mean squared error of 2%. So we could predict all the entries to within 2% of accuracy, even though we were looking at a tiny fraction of its entries. And the reason is, of course, that this matrix is well approximated by a rank 2 matrix. Since if I take the original matrix and I look at the truncation of the SVDs that only keeps the top 2 singular values, then it's a very good approximation, meaning that these temperatures are very low rank. Okay. All right. So now, what is kind of nice about this this line of research is that you have some theory, just like in the spirit of the IT community, where what makes IT work interesting is that you have some beautiful theories, some beautiful applications, and some nice algorithms, like the Viterbi who gave the name to this school completely illustrates this point. And so a lot of us in the field are trying now to develop algorithms to solve this minimum nuclear norm problem really fast. So they are semi-definite programs. The problem is if you use an off-the-shelf solver, you're not going to be able to go very far. You can solve problems which are about 100 by 100, but it's very difficult to go beyond this scale, and it's extremely problematic because we're interested in very large-scale problems. And so we've got a whole crowd of people developing specialized algorithms for minimizing the nuclear norms under all kinds of constraints. And so there's lots of people working in this field, making daily contributions almost. And so it's a very active field in numerical optimization to be able to minimize the nuclear norm subject to convex constraints. So I will show you just an idea of like the kind of things you can hope for, showing you that the theory works in practice and numerically we're getting there. So here is, can you read this MATLAB script? Okay. So because it's a summer school, I thought about giving you a little MATLAB script. And so what this is, I'm going to do something very simple. I'm going to create a matrix which is 1,000 by 1,000. So it has 1,000,000 entries that I wish to recover, but it's of rank 10. And the way I do this is by multiplying a random matrix which is 1,000 by 10 with another one which is 10 by 1,000. So I create a rank 10 matrix with 1,000,000 entries. The number of degrees of freedom is the expression we've already seen. It's simply the rank times the sum of the dimension minus the rank. So that's really the irreducible number of parameters I need to describe a matrix of rank R of this size. And then I'm going to show you that this really works well. So I'm not going to take a log oversampled. I'm just going to take 5 times the number of degrees of freedom. So the oversampling is 5, and then I'm going to reveal to you m entries, which is simply 5 times the number of degrees of freedom. So 5 entries per degree of freedom. That's it. Okay, and then I'm going to solve the problem with the singular value thresholding algorithm that has been introduced by myself and 2 co-authors to solve this problem. And so this is what this is here. So we have 5 entries per degrees of freedom. We're trying to guess all the missing entries, and there are many, something like 900,000 are missing. So we're going to try to find those 900,000 missing entries by semi-definite programming. And so this is a little script that is running. So our algorithm is an iterative algorithm. Okay, so it goes through several iterations. And so you have the estimated rank after every 5 iterations. And then you have some kind of stopping criterion that you see on the right-hand side. And what we see that the algorithm finishes after 140 iterations, roughly in about 19 seconds on this laptop, and holds an answer, which is essentially hopefully the minimum nuclear norm solution. And what we need to do is to see is how good is this answer. And so to see how good is this answer, we're going to compare the recovered matrix with the truth, which is what this little script is doing. And so I can make this script available to anyone interested. Okay, and so what we see is that the relative error is 1.8 10 to the minus 4. So I recovered all the entries within 4 digits of accuracy. If I were interested in the relative error not in the Frobenius sense, but in the spectral norm sense, it's also 1.8 10 to the minus 4. So essentially, I recover all the entries to 4 digits of accuracy from about 90,000 entries here in about 18 seconds on the laptop. So that you can see that, because of these efforts and efforts of many others, we can think about using these tools on fairly large data sets. Okay. All right. Okay, so there's many CPU tables showing you how well we do. For fun, with a grad student at Caltech, we implemented this in a parallel fashion using MPI. So that's a parallel C implementation. We run the algorithm on a 4-core CPU clocked at 2.4 gigahertz. We threw a very large data problem at this CPU, essentially a matrix which is 30,000 by 30,000. That's 1 billion entries that you need to recover. You're very close to Netflix size. Netflix size is 10 billion entries, or 5 billion. So you're a factor, an order of magnitude of the Netflix size, but you have a single core CPU. You observe 0.5% of the entries. The matrix is of rank 10, and we could get the same 4 digits of accuracy in about 3 minutes and 15 seconds on a 4-core CPU, which means that really we're starting to get close to be able to use these methods on real problems. Okay, any questions about this? Okay, so there are some theory, but as your questions pointed out, this theory is incomplete. I mean, we know something. There's many things we don't know. There are some algorithms, and people use this stuff in all kinds of applications. Now I would like to move on to the second part of this lecture, which is now we're going to assume that the entries are not only missing, but they might be corrupted as well. And that's going to have the flavor of error correction, of course. Okay, so I'm going to follow the same outline, which is I'm going to motivate the problem first, then I'm going to talk about the information theoretic aspects and some practical aspects. As for some reason, as you'll see, this error correction over low-rank matrices has an enormous amount of applications. And people are really flying away with these things. Okay, so the motivation. When I say that the Netflix matrix is low rank, it is true, except that unfortunately this is not what I see. It so happened that if you talk to people, there are entries that are revealed, that is, that people have rated movies, but some users sometimes enter completely bogus entries on purpose. And don't tell me why they do this, but they do. Maybe they don't want Netflix to do well. I don't know what is their agenda, but there are lots of entries. For example, there is a guy who has rated 18,000 movies. And I don't know how it's possible. Okay. And so there are like bogus entries, and I think a more sophisticated model for the Netflix problem would be that you actually observe samples of the Netflix matrix of which a fraction has been corrupted. When you deal with web data in general, the number of errors that may occur in the data set is quite large because some people are malicious. They will enter wrong data points on purpose. So you don't really want to fit a low-rank matrix to all the data you've collected. You want to fit a low-rank matrix to portions of the matrix and ignore the ratings that have nothing to do with the true user's preferences. So a better model for the Netflix problem should be that the data matrix we have is really low rank plus sparse. Low rank because of what we've seen before, and sparse because we've got these users entering bogus entries. Okay, and so in other words, what is it I'm asking here for? I'm asking, okay, now I've got some entries. They are incomplete, but some of them have nothing to do with the original samples of the matrix I'm interested in. And can I deal with this? In other words, can I make matrix completion extremely robust vis-a-vis these errors that we see in every data set? Okay, and that's very important to do this for practical reasons. And so whenever we do data analysis, whether there are images, video, text, web data, just like at the beginning, we would like to be able to recover the low-dimensional structure in this data, but we have to deal with the fact that most data sets are corrupted. That is, we have non-ideal observations. So if we think about the columns of a data matrix, it's very rare that these columns are good columns, in the sense that if I have a data matrix and I look at a column and I think about the columns as points in high dimensions, perhaps they span a low-dimensional space, that's for sure. But the problem is that there are lots of errors in these columns. Lots of entries in these column vectors are incorrectly recorded. And before I do low-dimensional recovery, I need to find out which are which, whether they're good entries or bad entries. And so this motivates the problem that we see here, which is now we're going to assume that no entry is missing first, and then we're going to assume that both entries are missing and corrupted. But let's assume that first there are no erasures. And so now you see a matrix M, which is a sum of a low-rank matrix and a sparse matrix. And why? Well, I have a low-rank matrix, which is the matrix I'm really interested in, but it's been corrupted by a malicious adversary who took some entries of the matrix and messed them up completely. Just like what you have in error correcting code. Okay, so now it's a very funny error correction because I have a sum of a low-rank thing plus a sparse thing, and my goal is, can I recover the lower dimensional structure? Then can I separate the low-rank part and the sparse part? In other words, can I detect what you've messed up? Okay, so of course it seems daunting, but not to this crowd because we know that error correction is possible. It seems daunting, and I say that a solution would be great. And so I'm going to open a parenthesis here and say, why is a solution would be great? A solution would be great because, are you familiar with principal component analysis? Not really? Okay. Okay, principal component analysis. What is it? You get a data matrix M, and you assume that this matrix is the sum of a low-rank matrix and a small perturbation. And what you want to do is recover the low-rank part. See? Another way of saying this is I give you points in high dimensions, and you can think about these points are being sampled from a low-dimensional place plus some noise, some little noise. And you want to recover the low-dimensional space. Hotelling introduced principal component analysis, and the way we do this is by trying to find a matrix of rank K, which is the closest as possible to the data matrix. And under this rank constraint, it looks like it's a hard problem, but it is not a hard problem to solve numerically because the solution is given by truncating the SVD. What you do is you take the data matrix M, you calculate singular value decomposition, and the best approximation to the original data matrix, the best approximation of rank K, is simply in this sum, discard the part corresponding to the smallest singular values, keep the largest, and that is the best approximation. Okay? And it's a fundamental statistical tool. Every undergraduate in America taking a course in statistics learns about PCs. If you Google PCA, you've got many millions of hits. Okay, all right, so it's a very big tool. But the problem is that PC is extremely sensitive to what in statistics we call outliers. And so here I took a bunch of points and I plot them, and I assume that these points span a low dimensional structure. So because I can only draw in 2D, they span a line like this. Now there's this blue point here, and suppose that a guy has incorrectly recorded the y value of that point, such that the y value is very big and very negative, and so that this point now in physical space ends up being here. And now the interpretation of the first principal component is you give me a cloud of points, and the first principal component is the axis, it's a line, such that the sum of squares of distances to that line is minimum. So if you think about it, if points are houses on a map, this is Main Street. Okay? And now you say, what is the line that minimizes the sum of the distances to the square? And now it's this line. Okay, so principal component, all the points are good. You would like to recover this line because you would like to detect that this was an error and recover this line. But when you run principal component analysis, you get nothing like the low dimensional structure you're looking for. You get something that has nothing to do with the original low dimensional structure. And that's what everybody, a statistician knows, is that PCA is extraordinarily sensitive to outliers, just like linear regression is extremely sensitive to outliers. And it breaks down with just one error. Completely breaks down. And that is a problem because in modern data sets, we have all kinds of gross errors introduced in data sets. For example, my two colleagues, so I should say that the second part is joint with Xiaodong Li, who is a grad student at Stanford, Emma and John Wright, who are two wonderful computer vision people at Microsoft Research Asia. And so my colleague working in computer vision or image processing, what they've got is they've got to do with the fact that they have gross errors, and for them gross errors are typically occlusions. So here's a very fundamental problem in computer vision is to do face recognition. And when you do face recognition is very hard, and the first step that everybody does when doing face recognition is to reduce the dimension by some kind of principal component approach. The problem is when you take faces of people, you have shadows, you have specularities, and so you have a lot of gross errors, which means that to find a meaningful low-dimensional projection, because you have these occlusions, because you have this gross error, is extremely delicate. And that's why face recognition doesn't work, is because we don't know how to project reliably when we have non-idealities. So for example, suppose somebody is wearing sunglasses, or a part of the image has been occluded, then you can imagine that when you try to do projections based on data of this nature, you get complete garbage. And you do. And so in real applications, we have to deal with the fact that people enter data erroneously or perhaps maliciously. We have occlusions in images. We have sensor failures. In a lot of these data sets, we have big errors, and that we need to be able to recover the low-rank part in the presence of these possible adversarial corruptions, just like in error correction. And so we have this model where we have this data matrix, it's the sum of the low-rank part and the sparse part. We might be interested in recovering the low-rank part, like in the Netflix case, but sometimes the component of interest might actually be the sparse part, as in some of the examples that I would like to present. One application that is interesting is in the area of video surveillance. And so in video surveillance, a big problem is like we'd like to separate the background from the foreground. So here is an image taken in an airport, and what you would like to do is, given a video sequence, you would like to have an automated system that is essentially separating the foreground from the background, the foreground being these people moving around the airport, the background being the background. And so that is a very important problem in computer vision these days. And so how do we do this? Well, one way we can think about this is via this kind of decomposition, low rank plus sparse. So if I were to stack the images as columns of a big data matrix, I could imagine that the low rank part corresponds to the background, because the background is not changing over time. And so the consecutive frames of the background are going to be extremely low rank. And I can hope that the low rank part of this data matrix is the background. And of course, the foreground, which are these people moving about the airport, are sparse disturbance in this low rank background. And if I can actually pick them up, if I can pick the sparse component that is not fitting this low rank landscape, I might be able to do separation between background and foreground. Okay, so that's another separation problem. There are problems in in graphical models, which are very, very cute. Do we have people familiar with statistical graphical models? Okay, so maybe I'll skip this application, which is a very cute application. I'll tell you the punchline though. So you have a graphical models, and what this graph encodes, it encodes a conditional dependence between nodes. Okay, so let's go quickly over this. So for example, x3, given all the other variables, only depends on its neighbors x1, x5, and x4, but not on the other variables. So people use graphical models to encode dependence between variables. Okay, so if you want, it's the extension of like Markov. Okay, all right. So this is a graphical model, and so we have an edge if and only if x3 and x5 are depending on each other, conditioning on everything else. Okay. Now in signal processing and in many other areas of applied science, people talk about graphical models with hidden variables, state variables that you cannot observe directly. So this is represented by this graph where at the bottom we have observed variables, and on top of it we have hidden variables. So the black variables are observed, the unobserved, the hidden variables which are somehow linking these variables together are unobserved. So we have a model with observed variable and hidden variable, and for this model we can actually write down the, so typically people, of course, in these models will have a sparse graph that is, the conditional dependence between variables is very few edges compared to the total number of possible edges. Okay, so now we have the covariance matrix here, which is essentially the covariance matrix of the observed variable, the covariance matrix between the observed variable and the hidden variable, and the covariance matrix between the hidden variables. And what we'd like to do is we'd like to recover the graph structure. That is, we would like to know, conditional on everything else, which observed variables are depending on each other. But the problem is I don't get to see the hidden variables. And this is where there's a very beautiful decomposition, which is essentially the Shor's decomposition, which says the following, that if I observe the covariance matrix of the observed variables, this is something I can observe because I get to see the observed variables, so I can calculate the inverse covariance matrix. The inverse covariance matrix is this matrix J naught plus this matrix. That's essentially a Shor complement calculation. And I just want to skip the details here, because what I want to say is that if there are very few hidden variables, this matrix here has low rank. The rank of this matrix cannot be greater than the number of hidden variables. So I have a low rank part, and if I have a sparse network, then I have a sparse part that I cannot observe because I have these hidden variables. Now suppose I could perform this separation. I could actually recover the sparse parts and the low rank part given their sum and their sum only. Then I would do something incredible, because what I would do is I would recover the network structure even though I don't get to see it. Okay? So if we could somehow separate the sparse parts from the low rank part, I could actually recover the conditional independence between the observed variables even though I don't get to see the hidden variables, which is a cute feat. Okay, so this kind of separation problem has lots of application, not only in statistics, but in graphical modeling, in computer vision, and so on. Okay, and it has many applications. People do document classification with this model, hyperspectral imaging with this model. There's lots of stuff that we could discuss, which we don't have time. Okay, so let's, now that we kind of see that it's of interest to given a low rank plus a sparse matrix, try to recover the low dimensional structure and the sparse structure. Let's see what's possible. So as a statistician, I get to see the sum of this low rank and sparse part. Well, the low rank part is completely unknown to me. I have no idea what the rank is. I have no idea. I know nothing about nothing. And the sparse part is also completely unknown to me. I don't know which entries you've corrupted. I don't know how you've corrupted them. I have no idea. Absolutely no idea. I don't know the magnitude of the corruption, so it's a bit different than what you do in your field, because for you, corruption, a 0 becomes a 1. Here is a 0 becomes 10 to the 80 or 10 to the minus 80 or something quite dramatic. I have no idea the magnitude of the corruptions. I don't know which entries you messed up. I don't know how many you messed up. I know nothing. Okay. But still, I would like to kind of see what you messed up. And so what I'm going to do now is I'm going to try to kind of recover the low rank part and the sparse part by solving, again, a convex optimization problem, which, again, is a semi-definite program. Okay, and so what we're going to do is we're going to minimize. So we're going to find it. We're going to try to find our best guess of what the low rank part is and what the corruptions might be. And to do this, we're going to solve a convex optimization problem. We're going to find a low rank part that has minimum nuclear norms. This is because of the low rank assumption we're making, which is what we've seen already. And then the sparse part, we're going to use a 1 norm for the sparse part. So we're going to try to find a decomposition so that the sum is what I observe. And among all this decomposition, I'm going to try to make the nuclear norm of the low rank part as small as possible and the 1 norm of the sparse part as possible. And what is the 1 norm of S? I abuse notation. It's simply the sum of the aggregate of the entries of the matrix. So this is a true matrix norm in the sense that it understands that L is a matrix and sum its singular values. This is not a true matrix norm. It looks at S as a gigantic vectors and just minimizes the 1 norm of this vector. Okay, this is convex. These are norms. It's a convex optimization program. It's, again, a semi-definite program. All right, so I'm just doing this, and lambda is a scalar. That's it. And the surprise is when I do this, the optimization problem will return exactly the low rank part and exactly the sparse part with no error whatsoever under very broad conditions. So what this is saying is you make up, Jack makes a low rank matrix, gives it to Gerhard. Gerhard mess up 10% of the entries, give me the matrix, I solve this, I'll see exactly what Gerhard messed up. There's no way I cannot see it just by solving this. Okay. All right, but of course, it doesn't hold in general. It holds under broad conditions. And what are those conditions? And those conditions are of the same type that the one we've seen, and that's why this part will go much faster, is because, so suppose you give me a matrix which is low rank plus sparse, but the matrix that you give me is this. It's a matrix full of zeros with a 1 somewhere. Well, this matrix, you give it to me and you ask Emmanuel, what is the low rank part and what is the sparse part? And I want to say that this question makes no sense, because this is both a low rank and a sparse matrix. So it could be that the low rank part is this and the sparse part is 0, or it could be that the low rank part is 0 and the sparse part is this, or it could be that the low rank part is half of this and the sparse part is half of this. How do I know? This problem does not have a solution. And so we don't want the matrix, the low rank component, to be sparse, because if you give me a low rank matrix which is both low rank and sparse, how can I separate it? This problem does not have a solution. And so we're going to assume that, well, exactly what we had before, that the low rank part cannot be sparse, which we're going to assume that the singular vectors are not too sparse, because if they were sparse, the low rank part could be sparse and we'd be in big trouble. So we're going to make exactly the same assumption as we've made before. We're going to assume that the low rank, the singular vectors, are not too sparse. They are not spiky like this. They're reasonably spread. Okay, that's the only assumption. All right, so now this low rank part is not crazy like this. And are we done? And yeah, we're not done. Because, okay, you give me a nice low rank matrix, and then can I corrupt it to make your life impossible? And you can. And how would you do this? Yeah, you remove a row. Exactly. So that's excellent. What you do is, Gerhard made this low rank matrix, gives it to you. What is your name? Iwei. And Iwei was very smart. What he does, he looks at the first column of Gerhard's matrix and subtracts it and gives me the difference. So I had a nice low rank matrix. He took the first column, subtracted it, so everything is zeroed out. When he did this, the rank did not increase, and it has carefully erased everything that there was here. And I hope you'll agree with me that there's nothing anybody can do. Right, it's gone. The information is just gone. You cannot recover it. Okay, so to avoid this kind of situation, we're going to assume that, yes, what we're going to do is we're going to give Iwei the choice of doing whatever he wants, but we're going to give him a random sample of entries to mess up, not a column or a row or a 2x2 block or 10x10 block, something that can make our life miserable. So what Iwei can do is it can mess up entries, but we're going to give him, he's going to sample a random set of entries, and then he looks at the low rank part. He can do whatever he wants, but he has to mess up a set of entries that has been chosen at random. Okay, and the result is this. The result is we have this low rank matrix which has this incoherence property we talked about. The important point is the rank can be very large. So we have a low rank part which is of size of rank n over log n squared. So the rank can be extremely large. It can be almost proportional to n. So we have the sum of a low rank matrix and a sparse matrix. The low rank part can be of rank n over log n squared. We can mess up a constant fraction of the entries of this low rank matrix. And what do? We solve this convex optimization problem. This is this guy with lambda equals 1 over square root of n. 1 over square root of the dimension of the matrix. Okay? So we solve this optimization problem with lambda equals 1 over square root of n. And what we guaranteed with very high probability, the probability is only over the set that you decided to mess up. With very high probability, L hat is equal to L naught, S hat is equal to S naught. So I will see exactly what has been done. I will be able to recover the low dimensional structure. This holds no matter what the magnitudes of L0 are, no matter what the magnitude of S0 are. It holds no matter what. What's remarkable about, what I like about this result is that this you can always run. I mean, there's nothing that you don't know that you need to solve this optimization problem. Lambda is universal, is 1 over square root of the dimension, and this will correct the errors exactly. And if the matrix was rectangular, the values of the scalar you have to choose is 1 over square root of the maximum dimension. Okay? So it works all the time with very high probability, and there's no tuning parameters. You just run these optimization algorithms, this convex program, and it will actually find those entries that have been corrupted. Okay, and in a way, this is a more subtle result than the previous one because, as you all know, it's easier to deal with erasures than it is to deal with errors. And so the thing between these two problems, which I explained at the beginning, is here we have missing data. Here we have corruption. That is, you never know whether a data point is good or bad a priori. And so you have to deal with this fact that it's not simply a fitting problem. You have to identify those data points that are bad. And the way you do this is simply by convex optimization, by minimizing the sum of this nuclear norm and this one norm. and it will find exactly all the entries that have been corrupted, remove them, and replace them with their true values. All right. Now let's see a bit how this works empirically. So we've done a lot of numerical examples, and this gives you a sense of what's going on here. First of all, it shows two things. Number one, that matrix completion is easier information theoretically than error correction. And then it gives you the range, the operating range. So on the right axis here, you've got the rank of the low rank part divided by n. And on the right axis, on the vertical axis, you see the fraction of entries I'm messing up. And then we solve a lot of problems by generating a matrix with rank n over 10 at 0.1, and I mess up 30% of the entries. And for each point in this figure, we solve lots of optimization problems. And then we looked at the fraction of times we did well and the fraction of times we failed miserably. When we did well, white means 100% of success. Black means 100% of failure. And you see there's a very sharp transition between the region where you do well and the region where you don't do well. And let's look at a data point. For example, suppose you give me a matrix of rank roughly n over 10. Then as long as the number of corruptions, so you go up, as long as the number of corruptions is below 25%, this method works. That you recover everything, that you find all the corruptions and you recover this matrix of rank n over 10. Of course, as you reduce the rank, you can tolerate more and more corruptions because somehow you have to recover a simpler and simpler object. And when you increase the rank, of course, the fraction of errors goes down. And so what it says is that there's a whole range where these things works very well, where you see that the rank can be proportional to n, the fraction can be very substantial, 20, 25%, and still you can actually completely find the errors and correct them. This is the range where matrix completion works. Row S here is being the fraction of entries you don't get to see, and what we see is the white region is much larger because, as I said, it's easier to impute than to correct. Okay, but what it shows is that the number of entries that have been messed up can be quite large, even in situations when the rank can be very large. Okay, so there is a parallel result that is due to Sangavi, Parillo, Wilski, and Chandrasekaran. It's very different from what we're doing here. But it's a contemporary result that is a deterministic result. And these researchers wrote a very beautiful paper, which is a bit not as explicit as what we have, where they establish conditions under which this separation, this perfect separation occurs. And it's a very beautiful work. It's deterministic, but the problem is it's very hard to see the operating region when this occurs. This is defined in terms of quantities that are difficult to compute, or if not impossible to compute. There are some cases where we can instantiate their results, which is a case where the matrix has some incoherence and the entries are the location of the corruptions are random, in which case what their results show you is that you can correct a fraction of errors, which is unfortunately less than square root of 1 over the coherence times the number of degrees of freedom. And what that says is that you cannot get in that range where the number of errors is fixed, that the fraction of errors is fixed, like 10% or 20%. Because what this is the fraction of corrupted, even if the rank is 1 and mu is 1, so you have in the best possible case, you can only have a fraction of errors which is 1 over square root of n, whereas we can have a fraction of error which is just constant, which is a very different result. And so even though our papers look at a similar problem, there's not much in common between these two papers. One is deterministic, the other is completely using random IDs, and so there's not much in common. Another point of departure is, of course, that we have a value of lambda, which is 1 over square root of the dimension, that is guaranteed to work, whereas for them, they don't tell you what the value of lambda is. Anyway, okay. And now we can put them together. And of course, in general, you may have entries that are both corrupted and missing, and that should not be a big problem. What you do is you simply minimize the same objective functional, subject to now the sum being what you've observed only on where you observed it. And the, oops. Okay, so what did I do?
I'm just guessing that's what happened. Is there a button on that thing that says video? Or?
Yeah, it's possible.
Sure.
Oh, okay.
Oh, you got it.
All right. Okay, and all right, and so now when we have missing data and corrupted data, I'll just tell you what the result says is we have a low rank matrix. We observe, I don't know, 10% of the entries, but that's completely arbitrary, of which a positive fraction are arbitrarily corrupted. Of course, the fraction that is corrupted has been selected at random. Then I set this value of the scalar in the robust PCA algorithm to 1 over the square root of the fraction of observed entries times the dimension, and what I'm guaranteed is that I will get the low rank part with no error. Okay, so I can essentially, you can give me a matrix, few entries of a matrix, of a low rank matrix. Where was this? Oh, sorry. Okay, so you can give me few entries of a low rank matrix of which a positive fraction are corrupted, and it doesn't matter, I will recover everything. Okay. All right. Okay, so when there's no corruption, we've seen that we minimize the nuclear norm, and that works. So if you have no corruption, you have a pure matrix completion problem. We've seen that minimizing the nuclear norm works. When there's corruption, there's something interesting that occurs, is that when we don't minimize this, we augment this with an S term, which can account for the corruptions. And when there's no corruption, this works equally as well, and that's kind of funny, because when there's no corruption, it will say that S is 0. So even though you did not know there were no corruption, it will actually find that S is actually 0, which is a bit unexpected. Okay. So let's look at some practical aspects, and then we'll conclude. So this is a bit more fun. So again, this is a semi-definite program. You can use SDP-T3 and current SDP solvers to solve this, but as before, you're not going to be very far in terms of scale. You're going to have a matrix size which is about 100, and beyond it will break. And for the same reason, a lot of us are trying to think about clever algorithms for solving this optimization problem on very large scale. And we've developed a non-standard augmented Lagrangian approach to solve these problems. And I'm not going to try to discuss these algorithms. These will be topics of a different lecture. I just want to show you one thing. So for example, suppose you give me a matrix of size with 1,000,000 entries. So it's a matrix of size 1,000 by 1,000. So I'm going to try to tell you what this row is about. So we have a matrix of size 1,000 by 1,000. It is a sum of a low rank matrix of rank 50, of which I messed up 100,000 entries. And now I'm going to run this principal component pursuit algorithm. I'm going to get an L hat and an S hat. The rank of L hat is 50. The number of non-zero coefficient in S hat is 100,000. The relative error is 10 to the minus 6. And we can compute this in 13 seconds on the laptop. And perhaps the more interesting number is this, which is if you can afford an SVD, then of course the cost of this algorithm is higher than that of SVD, but roughly speaking, how many SVDs do you need to compute to actually solve this optimization problem? And roughly it's 15. So if you can afford one SVD, you should be able to afford this algorithm roughly. Okay. All right, and then you can see that we can go to much larger matrices, much larger number of corruptions, and before I do this, I'm going to have to show you the little script that I have that does this. So first, I'm going to be very pedagogical. Okay, so now you're going to see that I'm not cheating at all, because you can reproduce this. So we're going to take a problem size which is 60. The reason I take 60 is because I want to use a wonderful program called CVX, which we'll call SDP-T3, and solve a semi-definite program for you, so you know that I'm not cheating. I'm going to I have a small scale problem. I have a 60 by 60 matrix. The low rank component is of rank 2, generated as before. Then I'm going to take 10% of the entries. So this fraction is equal to 10%. I'm going to select at random 10% of n squared entries by sampling. So m is 10% of n squared. I'm sampling m entries. S0, the corruption is 0, and then I'm going to put it, S0 of omega is going to be plus or minus 1, and I'm going to add them up. So, right, so what I've done is I create a low rank matrix, I create a sparse matrix, I add them up, I set lambda equals 1 over square root of n, and then I use CVX, and so what CVX is doing, so maybe we should see that. So I use CVX, and CVX is doing exactly what I'm asking it to do. I says, please minimize. So that's the beautiful thing about CVX, is that it knows about the nuclear norm. So you see how important of an object the nuclear norm is. CVX knows what it is. It knows that it's an SDP. And so I minimize the nuclear norm of L plus lambda, which is 1 over square root of n, times the 1 norm of S, subject to L plus S equals M. Okay, so we have our rank 2 matrix that has been corrupted. 90% of the entries are OK, but 10% are bad. And we solve this optimization problem. And at the end, we can see how well we're doing. That is, what is the relative error of the recovered L minus the truth divided by the truth, the sparse part minus the recovered divided by the truth, and so on and so forth. And so when we do this, we see that, of course, we completely separated the low, we completely corrected the entries because the relative error on the low rank part is 10 to the minus 11. The relative error on the sparse part is 10 to the minus 10. And of course, L plus S is equal to M. So the relative error is, of course, 0. So we recovered exactly the low rank part and the sparse part. Now, when I give a talk in statistics, you see that we have this norm, and this norm is balancing the nuclear norm and the 1 norm of the errors. And then there's this lambda that is balancing the 2 terms. And I don't know how many people are familiar with statistics, but typically when we see a lambda, we think cross-validation. Like, how do we choose lambda? Well, cross-validation. Here, there's no choice. Doesn't matter what is L, doesn't matter what is S. Lambda equals 1 over square root of n works, which is puzzling statisticians, to be honest. So it's very puzzling. And so what we're going to do is we're going to take the corruption here, and we're going to multiply it by 1,000. So now the errors were plus or minus 1. Now they're plus or minus 1,000. And naively, I would think that I need to rebalance the 2 terms. But of course, we don't. And so we're going to solve the same optimization problem, not changing lambda whatsoever, even though now the errors are completely on different scales. Okay. And so, all right, so it's going to solve the new. Now I just took the errors, multiplied the magnitude by 1,000. Maybe I should change something in the recovery algorithm, but I don't. I solve exactly the same optimization problem with exactly the same value of lambda. And so, as you'll see that the same lambda works universally. It doesn't matter what the magnitudes of these things are. And okay, by the way, you see each iteration is slow because it solves the Newton step. You can n equals 60 is fine, n 100 is barely fine, n equals 150 is not fine. It will just crash on you. Okay, and so we solve the same problem, and now we have an error which is 10 to the minus 9. It's perfect in my book. And 10 to the minus 11 for the other component. It's perfect in my book too. And so we're just fine. Okay, so now, of course, if you were to do this with n equals 150, the interior point solver would refuse to run. So we've developed an algorithm that just can deal with very large scale. So now we have exactly the same setup, but now n is 1,000. The rank of the low rank part is 45. We messed up 100,000 entries, and so the problem is to see what we messed up. So let's create this problem, and then let's use this iterative algorithm that has been customized for this problem, which is not an interior point method at all. It's an iterative algorithm. At each iteration, you see the guess of what the rank of the low rank part is, a guess of the number of errors, and then the stopping criterion. And so, okay, this algorithm converges in 14 seconds. And so it has guessed the low rank part up to 6 digits of accuracy, the rank match, everything matches. Okay, so it's all right. And so what's interesting about this is that in 14 seconds, you can correct 100,000 errors out of 1 million entries. And so again, you can start to think about using these methods for large data problems. Okay. All right. Chiara is my wife. She's always skeptical about what I do. She submitted a problem that was hard, where the size of the errors were exactly the size of the entries, so that it would be hard to distinguish, but everything worked. That's a piece of Chiara's matrix. That's a smaller piece on the left. You see Chiara's matrix. It's a sum of low rank plus sparse, the sparse being the color between plus and minus 1. And when you run this algorithm, you get the low rank part and the sparse part with no problem. Okay. So in the last 5 minutes, I want to show you some applications. And I think, if I'm not mistaken, I need to change the okay, all right. Can we lower the, because now we have images, so if we could lower the, turn off the lights a bit. Okay, so this is a kind of a problem. So now there are lots of applications of these techniques, and that this is the application in the area of computer video surveillance I was talking about. And I hope you can see these things well. So we stack the images as a column of a big matrix. We would like to perform the separation, low rank plus sparse, hoping that the low rank will capture the background and the sparse part will capture the moving. Yeah, that's good. All right. And so let's see how it works. So here we have this kind of video sequence in an airport, and we apply this algorithm, and we just look at the low rank part, hoping it's the background, and the sparse part, hoping that these are the people. And it's exactly what happens. You might ask, well, what is this guy in the background? It's because this guy is not moving on any frame, so algorithm is the background. And then you can see, of course, on the computer screen, you see much better than this, but you can see that the algorithm picks all these people moving about the airport. For some reason, the image don't display very well. We compare this with the state of the art in computer vision, and you'll see on the next one that that it's well, you can't really. So why is it that you can't really see this stuff? Is it better or not better? Or? It's better, right? No, not better. This is crazy. Okay, so I'll. Okay, this is better, right? Okay. Okay, so now we have a kind of a challenging problem where, you know, the illumination of this room is changing over time, because you can see here 5 lights are on, then 3, then 1. And so, of course, it means that the background does not have rank 1, it has rank higher. And you perform this separation, and the algorithm correctly identifies, you know, it understands that the changes in illuminations are part of the background features. And then you have this person showing up that exactly shows up as a sparse disturbance in this low rank background. And so you pick it up. And so you just, when somebody enters the room, boom, you automatically detect it. And when it leaves, S is 0. This is the state of the art. And you can see that this algorithm has a lot of trouble detecting what is low rank from what is background. You can do the same with faces. And so what's interesting here is, for example, lots of faces have, you know, very big shadows. You have shadows around the nose. You have the camera is saturating over here. You have specularities, meaning like bright dots in the middle of the eyes. And so I was hoping you would see these pictures a bit better, but essentially the low rank part is removing these non-idealities, treating them as errors. So like the eyes start to appear, the shadows are removed, and of course all these things appear on the sparse part. Okay, so this is actually even correcting for the camera is saturating here. I don't know if you see, but this camera is saturating. It's been corrected, and the saturation is over here. You see the specularities, which is this bright dot in the middle of the eyes, appear, and so this is essentially removing a lot of artifacts from face images. Then once you've got these artifact-free images, you can attempt face recognition. We've corrected old movies with this stuff. This is a perfect application for this. So, you know, like when you have old movies, you have lots of problems on the film which show up here. And when you look at the low-rank part, of course, it removes these things. So here you've got like this, and it's gone on the low-rank part. You know, here you've got these lines that are always in the old movies. They are gone over here. You have another line which is gone. These lines are going away. We've got like speckles that are going away. You know, this guy is gone, and so on and so forth. Of course, you have to be careful the way you tune this thing, because Tom Cruise better not disappear. So that would be bad. Okay. Now, in the last 2 minutes, I just want to show you. So my colleagues, they are very enthusiastic, and they're great people, and they love this stuff, and they think that it's changing computer vision, and they think it's a complete revolution in computer vision. Having said this, I want to say two things. One thing only is that computer vision is not like IT. People claim revolutions every 6 months. So you have to take this with a grain of salt, but they're very excited about this. And in reality, what this computer vision tells me, and I believe this, is that when you look at stack of images, they're not low rank plus sparse. They are low rank plus sparse after you do some alignments. Because if you take pictures of Emmanuel, Emmanuel is moving, and you don't register the face of Emmanuel, then you don't have this low rank plus sparse structure. It's only after you align faces that you can see low rank plus sparse showing up. And so what these people propose is, of course, to find a deformation of these images such that after deformation you have this low rank plus sparse structure. Now we leave convex optimization, we leave everything we know about, but heuristically there's nothing to stop us. We just try to find deformation of translations, rotations of images, so that after the deformation I have this low rank plus sparse structure. And how do I do this? I try to find the deformation so that my usual objective function is minimized. And this does quite well. So here's like some stuff they do with this. You take pictures of a scene from different perspectives, and of course you have like stuff occluding these features. And then you perform this separation, finding both the low rank and sparse parts and the transformation at the same time. And when you look at the low rank object, it's exactly the picture you're interested in without the occlusions. And the sparse part is, of course, exactly the occlusion. And so you can remove occlusion and do what people call in painting, that is remove occlusion and put what you should see instead. And you can do this even though you have different perspective. This is a picture of Al Gore speaking, and then you can do exactly the same thing. Now you stack these images in time, and you can see you can actually completely stabilize a video of Al Gore. It's not. I'll show you a kind of a weird example. Here's a weird example, and we like this example because we think that it could be the way why face recognition might work someday. Face recognition works very well in a control environment. If I take pictures of Gerhard, of all of you, and you go in front of this white wall, I put your head in a square, it's always the same lighting, and I put pictures of Gerhard 50 times, and of everybody 50 times, and then you show me a picture, I can have a system that says, this is Gerhard, this is what, Island, and I can do this. But the problem is, I'm not going to put everybody on the earth in front of a white wall and take 50 pictures of them. What you've got is you've got pictures of people under various circumstances. So here you see a guy. It's the same guy, but you see enormous shadows. He's wearing sunglasses. Here he has a shawl in front of his mouth. Here he's wearing a wig. Here he has his hand in front of his mouth, and so on and so forth. And then you perform this separation, low rank plus sparse. And the idea would be, if you did something good, it would remove the wig, it would remove the sunglasses, it would do all of this, and then I would see who this person is. And so you do this, so you look for the deformation and the low rank part and the sparse part, and that's the low rank part. And so let's look at this image, and it became this image. And indeed, it removed the sunglasses, it painted its face. Here you had a guy, he had a hat which has disappeared. Here he was wearing a wig, and of course all these attributes, the sunglasses, the hands in front of the mouth, the wig, they all show up here. And so now it's like you take an image, you completely remove all these non-idealities, the person appears, and of course now you may have a chance of recognizing who this is. Okay, they do a lot of stuff in the texture by trying to, so here's one of the things that they try to do. You show me a texture with a perspective that is not clear. It has a lot of noise because, as you can see, it's corruption. And what you would want to do is can you map back these textures so that you see it from, you have an aerial view of this texture. Okay, and here the idea is the same. You try to find a deformation, so you have this low rank plus sparse structure. And when you do this on real data, it works extremely well. So here's a picture of our president, and then you can actually look at the low rank part. So you undo this distortion. You can do this on textures. You undo distortions. You can do this on more complicated imagery. So here's how the algorithm works. You have an edge like this. You're trying to find this low rank plus sparse decomposition. And after you do the transformation plus the low rank part, of course, this has, once you transform it the right way, this has rank 1. This has rank 2. So this is exactly what you want. So you find the transformation so that you realign the textures the way you want. And so this is very, very important because it's a very important primitive in computer vision as a pre-processing step for any kind of recognition that I'm familiar with. You can realign textures with these things. You can take Chinese characters, it will straighten them up. You have a photograph of a page, it just completely straightens the page so that now you can actually do text recognition if you wanted to. Of course, you can straighten all kinds of objects by trying to exploit this low rank plus sparse structure. They're doing a lot of crazy stuff. Once you actually find the transformation, you know the orientation of objects, which is very important. So here's what they do is it's a Pisa tower, and you can make it straight. I'm not sure that's a good thing to do, but you can do this. And once you, of course, discover this process of straightening up textures, of course, you know their orientations, which means that you can map anything you want on top of them. And so there's a lot of applications in computer vision, in hyperspectral imaging, where people are using this low rank plus sparse model. What they like about the sparse structure is that you can deal with so much non-idealities in your data that makes the procedure robust vis-a-vis all the kind of imperfections we have in real photographs. And so they're quite excited. But again, this is a community that is excited quite often. OK, all of this works when you don't have low rank plus sparse, but you can have low rank plus sparse plus some noise. Nothing goes wrong. Something weird. Suppose a sparse component has random signs that when you mess up, you add a sparse component, but the signs of which are random. Then the theory said that the fraction of corruption entries can go to 1. The fraction of errors. S0 is not sparse anymore. It has 99.999% of non-zero entries, and still things are OK. And so I'm done. So what I try to convey is convex programming is unreasonably effective. You can recover matrices from incomplete sampled entries. You can recover those same matrices from incomplete and even corrupted entries. It's a emerging field with lots of algorithms, lots of applications. But as you pointed out, all of you, lots of open questions as well. And so thank you very much for your attention. Just one thing, sparsity, when I did my PhD thesis on sparsity, there were like 10 other people like me working on sparsity. Now it seems that if I want to publish a paper and sparsity is not in the abstract, that's a big problem. I think that low-rank modeling will become extremely important in for lots of years to come. Thank you very much.
Well, we are a little over time, but I think what we can do is we can move this lecture in the afternoon to start at around 1:15, since we have 15 minutes extra. Anyway, maybe we can have a couple of questions, if anyone would like to ask any. Yes, please.
So the matrix completion problem, or the matrix problem, for example, suppose I don't want to recur the entire matrix, but I want to recur one particular entry. Could you do sublinear time or?
I don't know. I mean, really, I don't know. To me, it's completely open. I don't know. You have to learn from everybody else, right? Everybody else is telling you something about that specific entry. You have to find the correlations in the data that allow you to make a reliable prediction. I don't know whether you can do this reliably without, I don't know. I mean, these are very important questions, and I have no answer at the moment.
What about infinite dimensional operators?
Oh, okay. So Sergio is asking about infinite dimensional operators. And you would see infinitely many samples, or?
Well, what is known?
Nothing. Nothing. In particular, there is the role of this log n, this kind of coupon collector effect might be a bit of a problem. But no, it's not been studied. Even in the compressed sensing case, a full analog version of compressed sensing is a bit in the works still. And here it's, for the same reason, it's not on the horizon.
Yeah, the person in the who put up their hand first in the pink shirt, please. Yes. Yes. No, you. Yes.
So when you're doing your measurements with corrupted data, for example, you have a person and she's wearing the sunglasses.
Mm-hmm.
And are you saying that you take your measurements with the person having the sunglasses on or off?
No, they are well, both. I mean, what you have is you have photograph of somebody under various conditions. Sometimes she's wearing a hat. Sometimes she's wearing sunglasses. You have 100 pictures of this person. The problem is now you have a new picture of this person. Now you have pictures of this person and pictures of other people. You have a new picture of this person, perhaps wearing sunglasses also, or something else, or a new non-ideality that comes up. Can you actually recognize this person? Mm-hmm. Now, I need several shots of the same person. I mean, I see one picture of you. I don't know if you have blue eyes or dark eyes. How can I guess? I mean, I can't. But what I need is I need a few shots of you under very different conditions. But I have, let's say, 50 shots of you. And then you show up in a non-ideal setup. And what this can do is it can actually make a prediction. Like what I'm going to see is I'm going to see L plus S, which is really you plus these non-idealities that you decided to wear that day. And I can remove S so I can recover you. But I need several shots of you. I mean, don't get me wrong. I mean, if I go in a museum and every time I go there's a veil in front of a painting, I'm not going to be able to paint what this painting is about. No, this I can't.
Okay, so there were two more. I think my brain was doing this low rank sparse. I saw a quick hand go up over there somewhere. And if it's not going to go up, then yes, the gentleman at the back, please.
In your theorem, you have probability of failure of SDP was polynomially small in N.
Yeah.
So what if you look at from another perspective, that for a given probability, failure probability, for example, epsilon, which might be another function of N.
Yeah.
Okay. Then we're going to give bounds on the number of measurements.
Right. And this theory is available. Yeah, this exists. So you fix the probability of failure delta, and then it says how many measurements you need. And roughly speaking, and the bound is like this. Like if you want a probability of failure, so roughly speaking, of n minus gamma, so I choose gamma equals 10 in my results, but gamma could be anything, then the number of samples is gamma times degrees of freedom times log. What you need, see the oversampling you have to do is logarithmic in the probability of failure. So if you, roughly speaking, it's like if you want a probability of failure delta, what it says is that the theory says that you have to oversample by log 1 over delta.
Okay, I think we'll stop there. Let's thank Emmanuel again for. And now we'll go to a group photograph. So let's all head out between the track